Hello, my name is Lieutenant Keith Ober. I am a medical physicist at the Armed Forces Radiobiology Research Institute. In this video, I will be discussing radiation detection equipment. Overview. The RDS equipment is composed of a base unit, probes, and ancillary support equipment. It is designed to replace multiple portable radiation measurement instruments or legacy equipment across the military forces. It is configured to support a range of smart detectors or probes and to display measurement results in a variety of units and formats. All probes in this system are considered smart probes and are powered by the base unit when connected to the base unit. Smart probes have a microprocessor, high voltage circuitry, and onboard memory. The type of probe and calibration information for each probe is stored in its memory. When connected to a base unit, a radiation measurement panel, an indication of the type of probe connected, will appear on the base unit home screen. Power or low voltage for a probe is supplied by the base unit via AA batteries, and the probe then generates the high voltage required. The common probe cable, which connects base unit to probes, carries only low voltages. This feature allows use of common probe cables of varying lengths without needing to recalibrate and enhances reliability. The operator does not need to adjust high voltage settings when switching between available probes. The probe can be hot swapped, meaning the common probe cable can be connected or disconnected without having to power down the base unit. RDS equipment utilizes Geiger-Müller or GM technology, scintillation, photomultiplier tubes, and solid-state semiconductor-based technology to detect the various forms of radiation. Detection capabilities are found in the base unit and in 6 different probes, each suited to different missions or purposes. To verify the functionality of the detectors in the base unit and probes, source checks are conducted using various check sources. These checks are to be performed as pre-operational checks, post-maintenance checks, and anytime an operator wants to verify the functionality of the detectors. The base unit manages 2 external interfaces, which are the probes and Defense Advanced Global Positioning System receiver. The base unit collects data from external probes when probes are connected. Here is the power button. Here is the GPS connection. And here is the probe connection. The GPS interface uses GPS Standard Serial Interface Protocol to add GPS information to data files collected by the base unit. The base unit also measures both low-energy beta radiation and photon radiation. It can measure alpha, beta, photon, and neutron radiation depending on the probe attached. When the field instrument for the detection of low-energy radiation, or Fiddler probe, is attached, some discrimination is available to allow the user to identify the likelihood of certain nuclear materials being present. The base unit is capable of displaying multiple measurements, units, and formats. When used with various probes, the base unit automatically loads the appropriate setup and calibration parameter from the connected probe. Connecting a new probe immediately reconfigures the instrument as necessary to support that particular probe. The base unit has operator configurable settings. It will automatically configure settings and load appropriate setup and calibration parameters from connected probes. Connecting a new probe immediately reconfigures the instrument as necessary to support the new probe. It is equipped with a beta window cap to prevent most beta and some low-energy X-ray radiation from reaching the detectors when installed. To detect beta along with gamma, simply pull this shield off the window. Detection capabilities for the base unit include detection of beta and gamma radiation. The base unit is powered by 4 AA batteries. this is where the batteries are inserted. Or by use of an AC-DC power adapter, which bypasses the battery circuit. This is where the AC-DC power adapter is inserted. The base unit is a microprocessor-based controller that controls all functions of the RDS by providing communications and low voltages to external devices. It has its own internal detectors and provides display and control capabilities for the entire RDS. It also contains ports for connections to interoperable equipment, as well as several auxiliary probes for specific additional detection capabilities. The base unit only supplies low DC voltages through the common probe cable to the probes. It is not necessary to power down the base unit to change probes. Probes can be hot swapped without damage to the probes or the base unit. Beta photon probe. The beta photon probe has two different detectors for low to high range dose and dose rate measurements. The low dose Geiger-Müller or GM tube is a gas-filled end-window detector sensitive to both photon and beta radiation with the beta window cap removed. The high range photon detection is achieved by a high dose GM tube. Removing the beta window cap at the end of the probe will increase sensitivity for beta radiation and low energy X-ray radiation. Similar to the base unit, here's the beta window, and here's how we remove it. Once connected to the base unit, notice how the display changes to show low and high ranges separately. The internal detectors of the beta photon probe are the same as the detectors in the base unit. This probe is designed to be used with the telescoping handle to extend the detection capabilities of the base unit. Here is the telescoping handle. As is in the name, the beta photon probe detects both beta and photon radiation. The end of the probe with a cap has a low-dose Geiger-Müller tube sealed by a mica window thin enough to allow beta and gamma radiation to pass into the tube. Inside the tube is a positive electrode or central wire and a negative electrode on the sides. Radiation enters the tube and ionizes the gas inside, which creates positive and negative charged particles. The negative charged particles migrate towards the positive charged electrode, and the positive charged particles goes to the negative electrode. This change in charged particles directly correlates to the radiation measurement. Sensitive gamma probe. The sensitive gamma probe enables detection performance for a wide range of photon radiation, but was designed especially to detect low levels of photon radiation. It contains a thallium-doped sodium iodine scintillator attached to a photomultiplier tube. The crystal in the sensitive gamma probe is permanently fixed to a PMT and is encased in an aluminum housing. The sensitive gamma probe detects photon, or gamma and X-ray radiation. Its high sensitivity makes it ideal for low radiation exposure. It is suitable for search operations to locate gamma sources. For the most accurate dose rate reading, point the sensitive gamma probe's end cap at the radioactive source. Alpha-beta probe. The alpha-beta probe enables detection performance for both alpha and beta radiation with a single probe. The scintillator material is in close contact with a plastic light pipe that is attached to a photomultiplier tube, or PMT. A replaceable mylar window is used to cover the scintillation material and prevent light from entering the probe. If the mylar window is punctured, the detectors will be saturated with light and will not be able to accurately detect alpha and beta radiation. As is in the name, the alpha-beta probe is used to monitor for alpha and beta radiation. Both alpha and beta radiation have a short range in air. Alphas travel about 1 to 2 inches in air, and betas can travel several feet depending on the energy. For betas, a good rule of thumb is about 12 feet per megaelectron volt, or MeV. Alpha and beta radiation monitoring must be performed with the front face of the alpha-beta probe in close proximity to the area being monitored for contamination. Its ability to distinguish between alpha and beta radiation enables the probe to generate data for each simultaneously. The probe operates on the principle of scintillation. It uses a plastic scintillator coated on one side with a layer of silver-activated zinc sulfide phosphor. The plastic scintillator generates visible photons in response to beta particles. The silver-activated zinc sulfide phosphor layer generates visible photons in response to alpha particles. The visible photons generated by the scintillators are measured by a PMT that converts the light into electrical signal. Lastly, it is important to ensure that the detector inside the probe is not exposed to ambient light. And again, the mylar window, which covers the detectors in the alpha-beta probe, is designed to block ambient light. Field instrument for the detection of low-energy radiation, or Fiddler probe. The Fiddler probe has a large diameter sodium iodine scintillator permanently attached to a large clear plastic pipe, which in turn is attached to a PMT. The scintillator is set back 2 inches from the face of the probe due to the addition of thermal insulation. This is a unique change to the design of the Fiddler probe from legacy Fiddler probes. The Fiddler probe detects and distinguishes between low-energy X-rays and gamma radiation. It simultaneously records data over 4 separate energy regions by use of a multi-channel discriminator. Analysis of this information can enable detection of materials commonly used in weapons of mass destruction. The Fiddler probe monitors 4 energy regions simultaneously. The base unit home screen has the ability to display 1 or 2 energy channels at a time. Fiddler energy regions: plutonium-239 X-rays in the range of 13 to 18 kiloelectron-volts or keV, americium-241 gammas in the range of 59 to 60 keV, uranium-235 gammas in the range of 143 to 220 keV, and a gross count of X-ray or low-energy gammas in the range of 13 to 220 keV. The gamma sodium iodine scintillator is installed in a large cylindrical housing that provides both protection against damage and thermal shock by supporting thermal insulation. The housing also provides a small amount of collimation. Collimation directs light into the scintillator at a known angle, creating a cone effect. Small area beta gamma probe. The small area beta gamma probe has a pancake configuration to provide a 15.5 centimeters squared sensitive detection area in a small and lightweight probe. The small area beta gamma probe detects beta and gamma radiation using a pancake GM tube. The probe is designed to be handheld and is suitable for operations looking for beta and gamma contamination. It can be used to search personnel or objects. A protective cover covers the beta window on the bottom of the probe, which is removed during operations. Hold the small area beta gamma probe in close proximity to area being monitored. The optional small area beta gamma probe shield can be installed on the probe to block radiation coming from other sources than the surface under inspection. Neutron probe. The neutron probe consists of 2 molded hemispherical polyethylene moderators. The neutron probe contains 2 different configurations of solid-state neutron detectors, one for low dose rates and one for high dose rates. A carrying handle is attached for the use during radiological operations. The handle has D-rings for attaching a shoulder strap. The neutron probe has a metal plate on the probe for orienting probe against flat surfaces during radiological measurement operations. The neutron probe is sensitive to neutrons coming in all directions and has a detection range from 0.25 eV to 15 megaelectron volts. It is surrounded by high-density polyethylene, a special plastic that is installed around the detector in order to efficiently slow high-energy neutrons to a detectable level. Neutron radiation is detected with solid-state semiconductors. The probe can detect radiation from any direction, but has a wall plate for holding the probe against a wall or flat surface. Geiger-Müller counter. This is a Ludlum Model 26 handheld pancake probe used to detect alpha, beta, and gamma contamination. It is sensitive for low levels of contamination. Here are some natural sources of low-level radiation that are in our everyday environment. Notice the reading and the auditory response as we evaluate these sources. This tile is coated with uranium oxide glaze. Also, here is uranium oxide coated Fiesta ware. Here is a small exempt cesium-137 source. Here is a piece of granite containing natural sources of heavy metals mined from the ground. Here are some lantern mantles which contain thorium. And lastly, we have the inside of a common household smoke detector, which contains Americium-241.